So here we have a probability distribution whose density function is given by this. Okay, so I'll leave you to verify that 0 to infinity e to the negative x dx is going to be 1, and of course e to the negative x is greater than or equal to 0 for all values of x. All right, and here we have 1. So what we have to do now is that we have to find the first quartile of this distribution, that is the value q, such that what we have is that the area from 0 to q should be how much? This area should be 0.25. All right. Or in other words, what we need is that the integral from 0 to q of e to the negative x, that should be how much? 0.25, or in other words, 1 over 4. So notice this, that what we have is that the antiderivative of e to the negative x is how much? Negative e to the negative x, and we are ignoring the constant because we are going to take the definite integral. So what you have is 0 to q e to the negative x dx, that is going to be negative e to the negative x from 0 to q. So we have this negative e to the negative q minus negative of negative e to the 0. So this is the area, or this area should be how much? 1/4 if q is the first quartile. So what we have is this, that is, we will just set this quantity equal to 1 over 4. So then what happens is we have e to the negative e to the q as 1/4 minus 1, or in other words, e to the, and actually I should have put, I forgot my negative sign here, e to the negative q is negative 3/4, which I'm just bringing it over here. So which is going to be what? E to the negative q is 3/4. Now we can solve for q by taking the natural log of both the sides. So on the left hand side we will have negative q times ln of e, and you know ln of e is 1. So q will be how much? Negative ln of 3 over 4. And if you just go ahead and take this as power on this by power rule of logarithm, you will have the first quartile of this distribution as how much? This would be ln of 4 over 3. So that's what the first quartile of the continuous distribution whose density function on this domain is given by this. Okay.